So, as we've talked about, one of the most striking features of Mars is this big difference between the northern hemisphere and the southern hemisphere. And again, northern hemisphere is like what compared to the southern hemisphere? Newer. I heard somebody say newer. Smoother. Younger. Lower. Okay. So we have this huge expanse of northern lowlands. The southern highlands are heavily cratered, therefore we know they're older. Something has happened to resurface or put a surface on the northern lowlands that is younger than the southern highlands. And one of the big questions of Mars geology is we see this phenomenon. We see this pattern in nature. Then that forces us to ask the question: well, how did it get to be the way it is? What are the processes that gave rise to it? What are the different hypotheses that we can describe for it? Okay, so again, we've talked about this already. This is just the MOLA data in Technicolor. The blue areas are the northern lowlands, younger. The reddish areas are the highest part of the southern highlands, the older cratered area. We also know that there's a difference in crust thickness between the two. So in the northern hemisphere, we have a thinner crust. And in the southern hemisphere, the crust is thicker. And it's more thick than just, everybody has the same bottom and the southern highlands are higher, therefore it's a thicker crust. The thicker crust actually extends down deeper into the mantle in the southern hemisphere than in the northern hemisphere. In general, you need to think of the crustal plates as kind of floating on top of the mantle. And so if the southern hemisphere crust is thicker, it's not only going to end up being higher than the northern hemisphere, but it's also going to be pushed down by the weight of the thicker crust deeper into the mantle. So that's a big obvious structure on Mars. What are the different explanations that we can come up with to explain why the northern hemisphere is low and the southern hemisphere is high? Okay, one hypothesis is impact. You can imagine that if there was an impact even larger than the impact that made Hellas Basin and Argyre Basin, it would make an even larger basin, and that whole northern hemisphere might just be one huge impact basin. That's one hypothesis, but science is most productive when we can come up with multiple hypotheses and then test among them. So what would be some other processes that would lead to all of the continental area, all of the thicker continental crust being in one area and all of the thinner crust being in another area? Okay, maybe it's volcanic activity. Maybe the southern hemisphere is like the Tharsis Bulge on steroids. There's been some huge mantle plume underneath the southern hemisphere for billions of years, and it has just built up a huge, thick cap on the bottom of the planet. Have we ever on the Earth seen a time when we've had all the continental crust put together and oceanic crust? Okay, when were those times? Earlier. Yeah. Much earlier on, so like Pangea, when all the continents came together. And what's the actual geophysical process that moved those continents together to form Pangea? Plate tectonics. So great, we've got 3 good potential hypotheses that all of them could explain why you've got thick crust in the southern hemisphere and thin crust in the northern hemisphere. It's like, maybe Mars got stuck in a Pangea-like collision of continents. Plate tectonics shut down, as we know it did, and it just, froze that way. Your question? I mean, it could be a potential, but you'd have to then explain, well, how could erosion have removed material from the northern hemisphere and deposited it on the southern hemisphere? So, weathering is something that should be considered, we should put it on the table, but it's probably the hypothesis we can rule out most quickly, because we can't think of many erosional mechanisms that would scoop material out of a lowland area and put it up onto a highland area. For reasons we won't go into, the geologists also relatively early kind of ruled out the idea that maybe it's just the result of huge volcanic activity in the southern hemisphere. So for a long time, there have been two main hypotheses, movement of crustal plates that got frozen once the continents were all together versus this impact theory. So how do we distinguish among those hypotheses? We can look at what we can see on Mars and see whether it's consistent with that or not. Clearly, plate tectonics and continental drift could easily result in this kind of formation. Check. But, if you're thinking about an impact, support for the impact theory, does the actual physical arrangement of highland and lowland, is that consistent with an impact? Bertram, you're shaking your head no.
What is impact theory distributed?
Yeah, so what is it about the shape of the northern lowlands that makes you think it's not an impact?
Well, I can't know, but I just feel like if it was, I just don't think it concentrates in a specific area. If it's being bombarded, then it would be being bombarded all around, rather than.
Well, it could be just one massive impact, right? And one impact has to happen somewhere. And the one impact could have been northern hemisphere. But I drew the kind of shape of the basin there. Does that look like a single impact? Because it's wonky. It's not circular, right? And we've been talking about, impacts are circular. But if we go to follow up on Bertram's point, well, maybe it was 3 impacts, right? And so people argued that, Sebastian.
I feel like there would be a central slump thing that you were talking about.
Yeah.
There kind of is a little bit, but not enough, not significantly enough for it to be like that.
Yeah, and then we also get back to the probability point. If the northern basin is due to 3 impacts, what's the chance of them all kind of hitting up there and not anywhere else? So for a long time, a lot of people poo-pooed the impact theory, and there was more support the fact that, maybe there was plate tectonics early, the plates kind of slammed together, plate tectonics shut down, and Mars is just frozen in a Pangea-like state. And we'll cover all of this stuff. So again, the main problem that people have raised with the impact hypothesis is the fact that we don't have a nice looking impact basin here. However, there has been recent research supporting the impact hypothesis. I'll just go through this quickly. If you take the globe of Mars and kind of flatten it out around the North Pole, in order to look at the shape of what that basin looks like in more detail, it does clearly not look circular as we look at it today. But, you know, this impact, if it did occur, would have occurred 4.2, 4.3 billion years ago. So what are some processes that could take a circular impact basin and make it non-circular over time? Let's go back to the volcanic activity. What is this large upland area here? Can you recognize it with Mars stretched out? Tharsis. Okay. So the thought then becomes, well, you know, maybe it really was an impact basin, but subsequently on top of that, Tharsis has occurred, pouring out all this volcanic material and making our what used to be a circular or at least elliptical basin now look all wonky. So how do you actually test that? Well, I don't want to go into the details, but you know, if you look at the gravity measurements that are being taken from orbit and look at the structure of Tharsis, you can kind of mathematically subtract Tharsis out from the surrounding landscape. And when you do that, lo and behold, you get this kind of estimation of what the initial basin could have looked like. Now, does that look like it could have been an impact? Yeah. Okay. So again, there's no necessarily no smoking gun here. The debate is not necessarily settled, but you know, this kind of examination of recent research has given more support for those that are proposing the fact that this really represents you know, an early, very massive impact.
Wouldn't something like really large like that kind of knock it off its like path, though?
Could well, you mean knock Mars out of its orbit? Not really. I mean, this if this were due to an impact, it would have been an impact that was slightly smaller than the impactor that smacked into the Earth to form the Moon. And you know, clearly that impact had a big impact, had a big effect on the early Earth in terms of probably changing its rotational speed. You know, we really have no idea what the axial tilt of the Earth was before this impact, but you know, afterwards we know it's been about 23 degrees from vertical. So yeah, clearly these very large impactors can have significant effects on their planet. Venus may have such a slow rotation because of the way it got impacted by large impactors early in its history. But yeah, generally speaking, an impact this large would not have sent Mars careening into the sun or flying out of the solar system. So I guess I want to just bring this up as an example of the use of multiple hypotheses we see something striking about Mars or about the world around us. We come up with these alternate ideas. We throw some of them out. I mean, weathering is something we need to consider, but it's not a good fit, so we can throw it out. Now we've got these other hypotheses. For some time, the evidence seems to favor plate tectonics more, but new evidence allows us to reevaluate the situation. And I would probably bet that when we get to Mars and actually start doing deep crustal drilling and so forth around the northern lowlands, we are going to find actual evidence in the rocks for the aftermath of a large impact. Jalen and then Sebastian.
Why is it that Mars doesn't have like a moon like ours?
Why does not? Yeah, that's actually was part of the argument against the impact theory. Mars has two wimpy little moons. Whether they are captured asteroids or actually accreted in place is another controversy, which we actually won't deal with in the course here. But, based on the angle of the impact and the size of the impactor, you may or may not get material thrown up high enough to coalesce into a large moon around Mars. This sweet spot in the middle in terms of not so steep, not so shallow angle, not so large, not so small impactor, is been identified in terms of computer modeling as the kind of impactor that would have just kind of folded the northern hemisphere back onto the southern hemisphere, making that crust even thicker than it was before, without throwing so much stuff into orbit around Mars that it coalesced into a large Earth-like moon. Sebastian.
I was going to say, another point is, the northern hemisphere has a lot less craters than the southern hemisphere. So would that mean that that big impact happened way late in the
No, it would not have been way late. If we
compared to the early bombardment period, would it be towards the end of that?
No, this would have been before Hellas.
So then, what are the chances that none of those why is there so much less in the north if that was an early crater?
If you look with gravity and radar sounding, there are actually craters in the northern hemisphere that have been covered over more recently. So the basin is old, if it is a basin. Whether it's plate tectonics or impact, the basin itself is old and has a long history of being smacked from space. Not to the same density as the southern highlands, so it is not quite that old. But something happened later to cover over those craters. And we'll talk in the next section on early Mars about whether that is, just the volcanic resurfacing, or if that's the sediments from an ancient ocean that have covered over those old craters. Okay, so you lucked out. I babbled on so long that there's no time for you to do the quiz. So I will see you on Monday. There are, I put up the readings. I will send out a course announcement about readings for Monday and Thursday for next week. But by and large, I will probably be out of communication over the weekend.
I forgot to get this to you Monday.
Okay, thank you.
Bye, guys.